Chapter 2, Atomic Structure and Periodicity. This is by far my favorite chapter. However, it might also be the chapter that you are probably going to be the least familiar with coming out of a high school education. So this is stuff that is going to get into the structure of atoms. We're going to talk about some quantum mechanics a little bit. It's going to be some new stuff. It's going to be some kind of weird stuff, but it is definitely doable. All right, so if you can dial a phone, you can handle this. And I'm sure that you are all going to be able to manage this, even if it's new stuff. We're going to talk about how atoms are built, what their electronic structure looks like, where do those electrons go on those atoms. We learned last time that if we've got a neutral atom, we've got a number of electrons equal to the number of protons. Like, where are those atoms going to keep their electrons? How are those electrons going to behave? And how does that then inform the periodic table, the periodicity of elements? What makes one element behave similarly to another? And we'll talk a little bit about the history of the periodic table as well. And we're going to start off with some sharks with lasers on their heads, because lasers are in fact going to come into this, if only briefly. So we're going to talk about the periodic table and what makes the periodic table periodic, and that is all going to come down to the electrons. But in order for us to talk about those electrons, we need to look at another subatomic particle, and that is the photon. And that's because the history of the electronic structure of the atom is intimately tied to the tool of spectroscopy, which is looking at different wavelengths of light. So we're going to look at electromagnetic radiation, the nature of matter, the atomic spectrum of hydrogen, which gives us the Bohr model of the atom. And we'll then talk about the quantum mechanical model of the atom, which is an improvement of the Bohr model. We'll talk about the quantum numbers that tell us where each electron is going to be located on an atom. We'll talk about orbital shapes and their energies, and then electron spin and the Pauli exclusion principle. And then we'll talk about polyelectronic atoms. So those are ones with more than one electron. We'll look at the history of the periodic table, the Aufbau principle in the periodic table, how are those electrons being built up, and periodic trends in atomic properties, and then the properties of a group. So we're going to look at the alkali metals and some of the other ones, because I don't think your book really does justice to have just one group of elements in there. Right, so questions to consider. Where do we get colors? Why do different chemicals give off different colors? If you do inorganic chemistry is one of the chemistries that you will do later on. Lots of great colorful compounds in there in inorganic chemistry. I do the lab for that. We make some stuff that looks like purple glitter and silver glitter and some orange compounds. It's very school spirit for us. Some nice superconductors, so lots of cool stuff with different colors. The field of electromagnetic radiation includes many different types of radiation. Right? Visible light is only a small component, a small fraction of our electromagnetic spectrum. And all light travels in waves. And we've known that for quite some time, that light acts like a wave. So to give you an idea of what this looks like in terms of scale, so photons of different energy are going to have different wavelengths. So that's part of our electromagnetic spectrum. They're electromagnetic waves. And they can go from very, very short wavelengths, high energy photons, or high energy light, like gamma rays, all the way down to long wavelength, low energy photons like radio waves. So radio waves have a wavelength of about 1 meter, so they're roughly human sized. Microwaves are 10 to the minus 2 meters, so roughly the size of a fingernail, 10 to the minus 3 for a pinhead or dust, or getting into the infrared. As you get down into the visible region, now you're talking about a range between roughly 400 nanometers on the blue end to roughly 800 nanometers on the red end. And those numbers, you'll see them written down. We'll have a range to them. This one's going 380 to 780. Different people have different expressions for the photoreceptors in their eyes, and so they're going to see different ranges and perceive colors a little bit differently. So some people can see down to 800 nanometers pretty well, and some people just can't see out to 380 either. So there's a little bit of a shift there. But the wavelength of light, those photons, are going to be roughly the size of a bacteria, right? So somewhere around bacteria size. we're looking at stuff that's in the hundreds of nanometers region. Smaller than that, ultraviolet's roughly the size of a virus. Atoms are down here around X-rays, and gamma rays are really, really small, right? And there's a correlation between the length of the wave, the color of the wave, its energy. So these things are all kind of interconnected with some of our wave-like properties. So here is a pro tip. So kind of stick this nugget of information in the back of your head, is that visible light is in the range of 400 to 800 nanometers, and it's going to have a frequency somewhere around 10 to the 15 hertz. Right, so that's roughly where we're going to be working most of the time in this class, is going to be in the visible. So if you see something that's like 10 to the 10th hertz, right, that's somewhere in the microwave range, or something like 10 to the 18 hertz, yeah, that's coming out as an X-ray. That would be a clue that maybe I might have solved a problem wrong. Same thing like if you're given a clue that if it's going to be visible and you get something that's 100 nanometers, now that's outside your visible range. So kind of know what those parameters are, and that's going to help you out. So let's look at what electromagnetic radiation looks like. So it is what we call a self-propagating wave. So there was a big debate back in the 18th century. We knew that light would act like a wave, but sound waves, for example, need a medium, right? They're traveling through air. It's a collision of one air molecule into another. Or the waves at a beach require the ocean, right? There's molecules there that are carrying that energy along. But what do you do with a photon, right? What are you doing with like light, right? Light can travel through a vacuum. There's nothing there to act as a carrier for that wave. And it turns out that's because waves kind of carry themselves. They're what we call a self-propagating wave. So we have two components to our waves. One is an electrical or E field component, and the other is a magnetic field component. And if you know anything about electromagnetism, you know that those two things are interconnected, right? Maxwell's equations. And they say that, if you've got a power generator, right? So you've got a source of electricity. You're basically spinning a magnet, right, at a power plant, right? You're using steam or you're using coal to make steam. That spins a turbine. That spinning turbine has magnets on it. That oscillating magnetic field induces an electrical current. You could do it the other way, have your electrical field induce a magnetic current. So that's how an electromagnet works. So these two things are interconnected to each other, and so your electric field kind of propagates your magnetic field, and your magnetic field propagates your electrical field, and so your light is able to carry on itself in the absence of a vacuum. What they proposed at one point was that there was some sort of ether, some sort of stuff that was a carrier for the wave, and we couldn't see these light wave carriers, this ether, right? Mysterious stuff. All waves have a couple of characteristics. They are wavelength, frequency, and amplitude. Wavelength, which we give the symbol lambda, is the distance between identical points on successive waves, either peaks or troughs. Frequency, we give the symbol nu. It looks like a V, but this is the Greek letter nu. It's the number of waves that pass a particular point in 1 second. And then last, we've got amplitude. That's the vertical distance from the middle of the waves to the top of the peak or the bottom of the trough. So this is how tall it is. And so let's take a look at some examples. So here we've got like a red wave, a red photon, right? Some red light. And these all have the same amplitude, but you will notice that when you go from red to yellow to blue, the distance between peaks has gotten smaller and smaller. So red wavelength light is longer than yellow, and the wavelength for blue light is shorter than the wavelength for yellow light. The frequency is the inverse of that. So red light is low frequency, and blue light is high frequency. And we'll find out in a second, too, that those are also related to the energy, where red is low energy and blue is going to be higher energy. There is an inverse relationship between lambda and nu. So lambda is equal to 1 over nu, or you could say that nu times lambda is equal to c. So c here is going to be the speed of that wave. So our wavelength times our frequency is equal to the speed. So we're going to do wavelength in meters, or we're we're going to do it in nanometers. And then we're going to do our velocity. It's our velocity. Our frequency is 1/2 so the units there are per seconds or hertz. And then our speed is going to be meters per second. So C is defined as the rate of travel of all electromagnetic energy in a vacuum and is constant. We call that the speed of light, and that's 3.00 times 10 to the 8th meters per second. Now, our pro tip here is that says in vacuum. The speed of light can go slower when traveling through other materials, and it's going to go slower based on what that wavelength is. That's how we get and why we get rainbows. So red light is going to be going at a different speed through glass than blue light will. And red light will go through water at a different speed than blue light will. So you can watch the Rainbow Conspiracy Lady just because that's an amusing interlude. But if it weren't for the fact that light interacts with stuff that's not a vacuum in a wavelength-dependent way, we would not get that bending of light that is different for blue light versus the bending of light that is different for red light. And so we wouldn't be able to get rainbows at all if the speed of light were constant. So for example, let's do a quick calculation. The brilliant red colors seen in fireworks are due to the emission of light with wavelengths around 650 when strontium salts such as strontium nitrate or strontium carbonate are heated. Calculate the frequency of red light with a wavelength of 6.50 times 10 to the 2 nanometers, so 650 nanometers. So what we're going to do is we're going to convert wavelength into frequency using the equation lambda times nu is equal to C, or nu is equal to C over lambda. And when we do that, we end up with a frequency of 4.6 times 10 to the 14 hertz, which is right in that ballpark that we're kind of expecting for a visible photon. Let's look at another example. The blue light given off by a mercury street lamp has a wavelength of 436 nanometers. What's its frequency in hertz? Right? We're going to do our same equation where nu is equal to C over lambda, which is a great joke, right? So a photon runs into another photon, and it says, hey, what's new? And the photon says, C over lambda. See, now you'll never forget that equation. So we're going to take our C, 3 times 10 to the 8th meters per second. We're going to divide it by our wavelength, which is 436 nanometers. All right, so here's our conversion from nanometers to meters. So 1 meter is 1 times 10 to the 9th nanometers. Our nanometers cancel out, our meters cancel out, and we're left with units of per second. So 6.88 times 10 to the minus 14 per second, or 6.88 times 10 to the minus 4 times 10 to the 14th hertz. And you want to be able to, BAT, go the other way. So if I gave you something in hertz, could you give me the answer in nanometers? So here's another example, right? So pickle light. You put an AC current into a pickle, right? I have seen people do this. Honest to goodness, I am scared to actually do this myself. So you take 110 volts to a dill pickle, and you get a glowing discharge. That's because the sodium and chloride ions in the forks cause the sodium atoms to get into an excited state. When the atoms reach their ground state, go back to the ground state from the excited state, they're going to emit visible light at about 589 nanometers. That's the kind of yellowish glow that you see in there. Old style street lights were often sodium street lights, which is why they kind of got that yellowish tint in there. It's coming from sodium emission. So how do we know that light is a wave? Well, we're going to talk about diffraction. We know this from diffraction experiments. Diffraction is the result of light getting scattered from a regular array of points or lines. This scattered radiation produces what we call a diffraction pattern on bright and dark areas, so alternating bright and dark areas. Scattered light can interfere either constructively and produce a bright area, or interfere destructively and produce a dark spot. This phenomenon occurs best when the spacing between scattered points is similar to the wavelength of the diffracted light. So there's a famous double slit experiment, which is proof that light is a wave. So you take light, right? It's coming in as a nice plane here. It goes through a first slit, right? So it's going to act like a point source. And then there's another slit, this double slit, in a second screen, which then acts as 2 point sources. And so now the light is going to radiate out. We've got this blue line here coming from S2, and we got another set of lines here coming from S number 1. Right? And at some points, those light waves are going to have peaks match up with peaks and give you constructive interference, right? Or a bright line. And in some places, a peak will meet up with a trough, and that will give you a dark line. And you get this nice, actually kind of sinusoidal pattern of light and dark stripes. And so it kind of actually matches the sinusoidal waveform that you're putting into it. You can actually do your own narrow slit experiment, where if you take your fingers and this is finger number 1 and this is finger number 2, and if you kind of close one eye and hold them up next to each other, you will start to see a dark band in the middle. So it's your own little narrow slit experiment you can do to help prove that light is a wave. So the diffraction patterns are actually incredibly useful in a lot of other ways. In a technique known as X-ray crystallography, we look at diffraction patterns to tell us the structure and arrangement of molecules and the atoms within them. So this is one of the ways that we know what shape molecules are, particularly important for things like biological molecules. So how do we know what a ribosome looks like? Well, we do some X-ray diffraction. Or how do we know what DNA looks like? Very famously, Rosalind Franklin's X-ray image of the double helix of DNA. And you get these series of light and dark spots. It obviously takes a little bit of math and effort to go back and retranslate this diffraction pattern into something more meaningful as a 3D structure, right? The one we saw here is a very simple 2-dimensional structure, giving us a very simple pattern. Over here, we've got a 3-dimensional structure. You can actually buy like those little glasses that around Christmas time, that if you look at the Christmas lights, it makes it look like there's a snowman or something like that, or if you get the tips for your laser pointer, those are another type of diffraction pattern that you can build, and the laser gives you the different constructive and destructive interferences that give you the pattern back out. So when you get peak to peak, you get positive reinforcement, bright spot. When a trough and a peak meet, you get a decreased intensity and you get a dark